Hello, and welcome to another Safer Sim webinar. Today we have a researcher, Dr. Cheng-Bo Ai, from the University of Massachusetts at Amherst, and he's going to give us a presentation on the deflection angle effects on continuous driver performance along horizontal curves. And with that, Dr. Ai, I'll hand it over to you.
Okay, thank you, Don, and then thank you, Safer Sim, for giving this opportunity for letting me know, present what we have learned in the past a couple of years on these projects. And as Don introduced, deflection angle effects on continuous driver performance along the horizontal curve is the focus of this study. And then along the course, I'll talk about a little bit more about the history of this project, but really, my name is Cheng-Bo Ai. I'm associate professor in UMass, and then Cole Fitzpatrick is the research professor here at UMass. We co-PI'd on these projects. Dr. Elisa Ryan, Dr. Emily Hennessy, and Mr. Xinyoung Ye was involved in these projects, doing different pieces of this work. Okay. All right, this is the outline of today's presentation. And I'll just quickly introduce what's the background and motivation, some objective, and then go into the methodology we use, results and findings we have come up with, and then the missing piece that I want to discuss a little bit for future studies. Okay. So this is my favorite video, although not the consequence of this video, but what it shows, like horizontal curves is a very important subject for us to learn what's going on there, right? People drive on curves, although curve only occupied 5% of highway miles. 25 of the fatal crashes happened there. I mean, not only about the fatal crashes, all the other type of crashes happen more frequently along the horizontal curve, which is sort of intuitive and understandable because along the curve, you have more tasks for the drivers to endure. You have to watch the traffic, you have to maintain your course, and then the geometry change, which is understandable. But also, we want to look a little bit deeper about what exactly happened and if there are any specific characteristic or parameters that we need to pay more attention to. So that's the motivation, comes to the motivation. Roman curve is important, right? The average crash rate is really approximately 3 times the average crash rate at the tangent section. Although this is older documents, it still holds pretty true, actually, even more in recent years. But we don't necessarily know where are the horizontal curves. And then based on the conversations I had with multiple DOTs, based on the literature reviews, that there's really not a unified horizontal curve inventory files in their database. And then all the safety engineers, most of the safety engineers are really just working on their experience. And then not to mention about the geometries. Certainly when the roads were constructed, they know that exactly geometries. However, with the different preservations, maintenance, things change, right? You put an overlay and then your cross slopes suddenly change, or you change the modification of your line alignments, and then the geometry changes. However, not everybody is keeping track of all those informations, right? And also, most importantly, we have so many curves. Although we don't know exactly where they are, we know they're there. However, which are the ones more hazardous over others? Why there's crashes concentrated on certain areas of curves versus other? So that's the motivation. Really, these questions really bug me and my co-PIs. And just what should we look into? The other is from the driver's perspective. The drivers are likely to slow down, and based on the observations made by Texas A&M, TDI, they did a bunch of experimental field testings, and it's driver's perception, the roadway where the curve occurs looks different, right, or change, and then they slow down, which is a good observation. It means like people are slowing down. That gave, I guess, more response time or along the curve, which is great. However, we don't exactly know at what point they slow down or to what extent. To a little detail about horizontal curve studies that the TTI was doing, they put a bunch of observation points, and they know that which section of the road of the curve where the drivers are slowing down, but they don't know exactly where. And laterally, they have some kind of sensors to make sure we'll see whether there's curve cutting or not. But still, we don't know exactly for sure. And then, of course, this happens about more than 2 decades ago. And then we want to see if we can do a little more about that. So that's really motivated us to look into this particular study. So the objective, again, I'll talk a little bit about the history, but the original problem statement, which was really right around COVID hits, right? We want to investigate the relationship between the driver's behavior and horizontal curve with different deflection angles, because we thought deflection angle is one of the important keys for horizontal curve design, and also from the driver's perspective, it's changed. I mean, that's what they see. And then using driving simulator. When we say driving simulator is the full cabin driving simulator, we'll talk about at UMass. And then we have some experimental design drafted. We developed different works preparing for the driving simulator. And of course, everybody knows that the COVID hits. But what we were trying to do is there's no participants whatsoever in the past few years during the COVID. And then certainly later on, there's a few participants that certainly my partners snatched them up very quickly for their experiments. So this one get a fall behind. So what we're trying to do is, can we do something slightly different rather than using the driver simulator, but can we do some of the development of different tools so that we can still achieve the goal that we want to do? However, we don't have necessarily touched the participant parts, because these tools may create a bigger impacts in the future analysis, and then certainly can link with the driving simulator later, or not the full cabin driving simulator, but those kind of a simplified version of the driving simulator. Okay. So that leads to the 3 key questions that we want to answer in the study, and which is objective, and I'll leave them all. The first question is, what are the critical characteristics of the horizontal curve? And then that leads to the development of a curve context extraction tool that we have. And the second one is, what are the critical horizontal curves that we want to investigate? Because there are so many of those, right? So there's a geospatial analysis tool that we came up with using GIS to really knock that down, so we can find where would be the curve that we really want to simulate. Otherwise, you don't want to replicate the thousands of curves in the driving simulator, right? The last one is, now we have the curve, the characteristics. We identify the key curves that we want to look into. So how can we really create a realistic driving simulation scenarios, and how to better understand the driver's behavior along the curves, and then especially the one we want to look into, right? The horizontal, the deflection angle along the horizontal curve. And then we use Carla as a simulation scenario generation tool, which is really developed or advanced really fast in the past few years. But we use the simpler side of the Carla, the simulation, but I'll explain a little more about what exactly we did. But with that simulation, it's like a video game, right? And then we can use that to really investigate these kind of a simplified driving simulation scenarios, and then still identify the values that we want to extract. Okay, so I'll go one by one. I know I have 25 minutes-ish time. So the first one is the curve context extraction tool. So the tool itself is simple. As I mentioned, many of the DOTs based on our survey, we didn't have any of the inventory of where there are horizontal curves. They just know, oh, they're there. So what we did is, like, we took advantage of a algorithm that I developed many years ago, but implemented on a really network level. So to identify exactly where the curves are located, the curve geometry, especially the deflection angle with a very detailed measurements, certainly is also included in a slightly different scenario, because curves can be complicated with spirals and compound curve, right? And then also the type classification, which gave us even more detailed deflection angle measurements. So I don't want to go into the algorithm itself, because it was published before. But I mean, for those of you who are interested in, reach out to me, I can explain it more. But really, it's just a circular fitting process, right? You fit into different bunch of circular shapes and find the best arrow or lowest arrow, and then you figure, oh, that could be my radius, and then you adjust the parameter to move on to the next section, and then fuse them together where you find the convert to the minimum arrow globally, then you know, oh, my road is segmented perfectly. So, and this works like this. So there's a tiny animation, but you can see that by navigating the entire trajectory of the road, you should be able to identify where the curves are. And then just after everything is done, you reevaluate the entire length of the sections and then do a global arrow minimization. And then you get all the curves. Certainly when you do the circular shape regression, it's automatically generates your radius and then the deflection angle, right? Which is very handy. But that's basically it. And you have all those inventory the curve locations. And then the input of this can be multiple sources. In this scenario, actually, I use the payment marking extraction from the center line of the road, which came from the LiDAR scan. But it doesn't have to be the way that way. It can come from the base maps that most of the DOTs have access to, and then can generate a very similar process. Okay. Certainly, curves can be complicated because they have different shapes, right? Compound curves, reverse curves, and spiral curves. So we also have the classification methods. So for simple curve, it's easy. The deflection angle is just the center angle of that little curve, right? But for compound curve or reverse curve or the spiral curve, compound curve, for example, you have to combine the two simple curve or multiple simple curves together to find the deflection angle. And then for spiral curve, actually, it's kind of a changing. So that's the little tweaks that we need to deal with for those different types. But essentially, that's pretty much it. You have all the curve information identified. Just to give you an example, this is entire Massachusetts with it. And then there, if I remember correctly, there's a little over 10,000 curves, and then colorized with different level of classification of road. And then if you zoom in details, you can see the delineation of the curves, the radius and deflection angle, and then all the detailed curve parameters, middle alternates, arc length, all those are basically in the geometry design class that we have been experiencing, right? So that's all the details. And then now we have all the measures for deflection angle, which we are really interested in, right? So this tool has been implemented on a huge network, which I will show in the result part. But this is ready to use for any input trajectories of the road. Okay. The second part is, well, we have the inventory. Now we know where the curves are. We know what the parameters are, and also for DOTs, we also know where crashes happen, right? But we just want to know what's the linkage or what are the curves we should look into. So that's the geospatial analysis tool becomes handy. Okay. The goal of this tool is to identify the group level characteristics, which is a sort of like the goal we are doing, the deflection angle, or it can be something else, but in this scenario, in this study with the deflection angle, right, and how it affects the base level characteristics like a crash severity. So, and we did the experiments for Maryland and the Vermont just to get the we happen to have access to their data, crash data, but also more importantly is that they provide a little diversity in the different networks. But I'll show you later on the results. So this is the flow chart that essentially actually Elisa developed, and then you can see the integration of the data is the first part. We have this, here's just a summary tables of all the crash data, but also we have the individual locations of the crashes. And for those of you who work with the crash data, you know it's not clean. So we did a bunch of cleaning data, make sure all the data are in good quality, and then georeference correctly to the location. And then we also have these kind of a map, right? Curve map. So basically you superimpose these crash layers into your curve maps. you know their spatial locations, and you sort of can use the proximity to link them together so that you have all the linkage between the geometry or between the infrastructure, let's say, I should say, the horizontal curve geometry and the crash. And the crash behind it, you have the crash severity data, you have the location, you have the when it's happened, what involved, different classification of vehicles, etc. Okay, and then what we really want to do is we want to understand the grouping effects. When we say grouping effects, is like crash happened, it's all one-off type of thing, right? Each crash is unique, as you may say. However, what we want to say is it happens if there are any common themes, if it happens at a similar deflection angle or similar type of curves. And then different crashes may have other characteristics, but we want to know whether we can group a bunch of those into that location. And then we would know, oh, those locations are more prone to that characteristics of the curve. And in my case, it would be the deflection angle, right? So we introduce a model called a Bayesian hierarchical model, which is really just to investigate that grouping effects. Okay, so that's the model is trying to estimate the crash counts or severity depending on which one to want at each of these deflection angle category. Okay, so the model is work like this. There's a response, and then there is a P term, and then the group term, the G term on each given group. And then certainly the definition response would be the goal, right? What's the crash value of each curve? Either can be a crash count or can be crash severity. And the P term is the effects of that are the same across different observations. Here, observation by observation and crash, right? At the same curve, what are other different crashes happen? And then similar curves certainly have the same deflection angle. For the G term, it's just the effects that are various across the grouping variables. It can be something like ADT. And then the group would be for each specific curve, I want to bunch them together to that, right? So here is just a summary of these, I guess, the characteristics for the curves and for the ADTs. And certainly the structure is like that. The curve characteristics will link to the different crash characteristics. And what we want to understand is like, oh, by this curve characteristics, do we have a bunch of crash characteristics going under, which means is like at the root link that has something to do with the grouping effects. And then we want to know where would be the concentration of those grouping effects. Okay. So all the details are published in this paper last year. And not only that, we also remember we're stitching the crash data with the curve inventory data. So we also developed a GIS tool just to integrating them everything together. Okay. Remember the grouping effects. Here are the things that becomes interesting is you will have those kind of a contribution or the coefficients of that deflection angle to that location or to that curve, right? So you can see some of those are negative, which means that this curve doesn't necessarily contribute to any of the crash severity or the crash numbers, which means like this is not really related to that. So we eliminated those. And for the ones that are more related to that, we sort of added to the data sets that we want to investigate furthermore. Okay. I'll show you the details maps in the results section, but essentially you would generate a heat map of what are the curves that are more interesting to look at to understand how the deflection angle may play a role. Okay. So that goes to the third question that we are having is like now we have the hotspot. We know what are the curves we want to look into. We know the geometry of the curve, and we have some sort of descriptions of other traffics and other complementary data, right? We want to now it's time for us to create a realistic driving simulation scenarios and then see to investigate really how drivers are responding to those actual curves and with the certain deflection angle. That's where this scenario generation tool was developed. Okay, there are two pieces in this tool. One is the road generator, if you will, is we want to create the road, which is the base mapper for the driving simulator, right? So for those of you probably very aware of those. But besides the curve we inventoried, we also need additional geometries such as lane width or cross slopes. This comes to the I guess we query different data sources, including data we collect ourselves with LiDAR, so we can generate all those lane width and cross slope measurements. And there's a paper published a while back. I won't emphasize too much on that, but with that data, we can generate the input for the road creation. Okay, if you don't have LiDAR data, which is totally fine, you can always have the default values for generating those roads as well. So the second piece, or the second part of the first piece would be the Roadrunner, which is a software managed by MATLAB, right? So integrated with MATLAB, and then it generates the road geometry, and it can output to like open road or any of the open specifications for driving simulators. And then what we need to do is to grammatically in MATLAB to generate the two pieces. On the geometry, if you have the geometry itself, certainly the curve inventory we exported to the Roadrunner directly. And then for the additional geometries and terrains, we added more to the Roadrunner. So like I said, many of the curves we don't have LiDAR data, but we still use the default value to generate that. For example, the lane width, the cross slope, right? So there are also the third part of the first step is the other environment variables, whether they're signage, they're guardrails, they're all kind of things, and pavement markings. We didn't really manipulate too much about that. We just used the default value of the plain road, but that can be enhanced in the future. Especially if you have the LiDAR data, which another projects we're doing for mapping all the road furnitures, but that's a different story. So for the second piece is now the road is built, right? As shown in the middle part, you have the entire road geometries. And then you want to import it into some kind of simulation scenario. That's where we were trying to use Carla instead of the full driving simulator softwares to do that, because the Carla is sort of it was not developed really for simulation, for driving simulation per se. It's more of a testing automated features and get all the sensors feeds and then integrate with the vehicle's performance, right? However, we took a Carla because it gave us enough flexibility of doing the import of the model, but also have sort of a manual input. Okay. The manual input is directly derived from Carla. However, it's not very mature at the time when we start to really play with it. There's a manual control. I'm sorry about the typo. There's a manual control portion for that PY, for that code to really control the scenarios. So use your keypad. However, that's pretty much it. What we really want is we build the scenario using the true data, and then let the participants to drive in front of a screen, and then we can record, which is as shown is logging the data that the keyboard input. So we know exactly when the driver looking at the curves, and then on the back end, we know what's the deflection angle or other characteristics this curve is, and then we can record their response. So this becomes more powerful so that we can understand when they apply the brake, throttle, or steering. And also we can record the duration of the applications. There's the third model. We can also look into the intensity of these applications. However, in this study, we didn't investigate that more because Carla, we didn't develop the codes to look into the how much of the steering wheel is applied, because most of the scenarios would be based on keyboard, not on joystick. But if it were on joystick, let's say you are playing a Grand Theft Auto, for example, actually how much of that steering wheel joysticks would move towards one direction towards another can be recorded too. So that's what we did for these kind of recording. Okay. So this is just a very quick screenshot. There's a link there, and then there's a modified manual code. We're trying to actually revamp whatever the GitHub repository that we're having, but really what it does is running the model and then store all the corresponding data in terms of the human input or the driver's input, if you will, the participants input. Okay. And here is just a very quick spreadsheets of that input. And then you can see the simulation time, the location. And then what is the key is this part, which is all the key downs and key ups of these drivers, of where and when they applied. And then for the break, actually, there's a certain different levels of break that can be recorded. And certainly we link these with, because on the scenario on the Roadrunner, we build all the geometries. We know exactly where the geometries are, what it looks like, and where this action is happening during or after or before the curve, they can observe. And then we sort of link everything together so that you have one piece of information or one piece of the scenario that you can have all this information populated in the spreadsheet, right? So that's what this tools does. And one of the reason why I said this is a simplified is because along with the geometry information, so you have all those other attachments of other geometries that you may be interested in. And then here, certainly, we didn't include the vertical elevations in these kind of Roadrunner designs. We only usually introduce, introduce two design alignments, horizontal alignments, and also cross-sectional alignments. The vertical alignments was not within the scope. We don't want to complicate things, we didn't. But in the actual tool, we can incorporate the vertical alignment as well. Okay. So these are the three tools. I'm running a little more. These are the three tools we developed. As more of the details will be published in the report, but also we published 3 papers associated with that. But these, remember the first slides that I mentioned, we're sort of shifting from the actual recruiting participants doing this. Instead of, we spend more efforts on developing the tools, which can be a drawback for this particular study because we don't have participants records. However, on the other flip side is this tool is general enough to be applied to a bigger audience of when they do have rich sources of participants, and then we can let them use this and then do the test. Actually, one of the plan for this is to apply this to the summer high school program so that they can just play these games and then record those values because they are about to become the new drivers of the road. Okay. But these are just quick summary. There are more details in these papers and then coming up the report too. But I just want to show you some of the results like from those 3 tools. Remember, we did Maryland and Vermont, right? This can be done by other states as well. And then we investigate the road networks, identify these curves, and then we use these identification of curves for our analysis. Okay. And then for the horizontal curve instructions, although we didn't spend too much time on developing the tool because the core algorithm was there, but we did tailored a lot on these tools to make sure that it can work on different sources of data. And then so far we extracted more than 100,000 horizontal curves along the network. And then there's a batch code processing to convert it into the Roadrunner models, which means is like we have 100,000 horizontal curve scenarios that we can potentially let the drivers or participants to use. Okay. And here are just some of the examples of these curves that we extracted. You may recognize some of the states that you're in. So what's missing in the future study? So as I mentioned, the original problem statement, we didn't have any participants just because at the beginning, we don't have participants because of COVID. I mean, I always put blame to COVID, right? But which is good in the sense that we have the luxury to develop the tools. But to make sure this thing actually work in a larger scale or in, let's say, in a full cabin driving simulator as was originally proposed, we do want to include participants for testing these scenarios. And then this is, I guess, if there's a certainly I think at the time we applied for phase 2, but because we didn't have much results, we didn't ended up going to phase 2. But I do want to recruit more participants on this. I know it's kind of late for saying that the participants is the key, in which we realized that when we proposed, but we didn't realize the COVID hits. The other part is open sourcing. What we were trying to do is trying to open source the code that are from the Roadrunner. I know MATLAB is kind of it's not quite open source, but unfortunately Roadrunner got acquired by MATLAB. But what we're trying to do is we want to use open source this code, how we batch processing the horizontal curve we extracted, so that we can create that what we promised, that 100,000 or even more scenarios of different curves, so that it can be embedded into the Carla or whatever the driving simulator that we can maybe use. So these are the two things that I think for the next step to work. All of those tools, that are 3 tools I mentioned, are in good shape and running operational. And then, as I mentioned, I plan to release all of those to everybody. And the data, the curve data has been released already, actually. Well, not released, but the screenshots, the snapshots of those curves are released. So for the acknowledgement, I just want to thank the entire Safer Sim family, Don, Jacob, he left, but I mean, everybody in this consortium. I sort of joined this family late, but I think that this is a really friendly family, and I would love to see more of UTC like this to be happening down the line. And then certainly the UMTC family is treating me really well with this, with all the support of data and the crash data, as well as access to the driving simulator, even though we didn't ended up using it. The research team, I mean, Alisa, this project's a kind of a dragged too long. I'm sort of put blame to COVID, but I mean, the good thing is that they came up with, I was lucky enough to have these kind of talented students to work with me on different parts of these tools. Alisa right now is an assistant professor in University of Arizona. Emily Hennessy is in Federal Highway Administration. Xin Yang is back to China. Wusong and Andy, they're in the IT companies. Wusong is in a bigger consulting company. So these are actually the experience, and certainly thanks to their hard work to make these things happening. And then the last but not least, I do want to mention Xin Yang, who is actually got involved within the projects from the very beginning. However, he was suffering with some of the mental and the physical distresses. So, but he still stick with me from the beginning. And then I'm happy to report that he just recently graduated after 4 years. He just recently graduated as a master's student. So kudos to him. But other than there's many others I would like to thank too. But I am running, I guess, way out of time. But here's my contact information if you need more information about any pieces, and certainly the report will be soon be released. And then for the published papers, it's there already. But with that, I'll just stop here. Don, sorry for dragging this a little longer than you planned.
Oh, it's quite all right. I'd like to open the floor up to any of the attendees if they have any questions. You go ahead and unmute yourself.
Thanks a lot for the presentation. Maybe I had a question. I was wondering, during this work you've done, have you identified the areas of these curves that perhaps didn't follow AASHTO book rules or any other proper road construction? And have they been separated or no?
That's a great question. Officially, we didn't do many of the compliance evaluation. We didn't do whether it's meeting and because of 2 reasons. One is because AASHTO's design guide is not mandatory, so you don't necessarily have to follow that if you have a good justification, although it's highly recommended. The other part is related to the data that we're getting. Right now we treat each curve individually. because many of those compliance, for example, broken back, whether the curves are continuous or not, those are the things that are related to the connection of different curves. And then on top of that, also whether the curve is in compliance or not, or whether meet the standard or not, have very critical information related to the design speed. We didn't consider any of the design speed in these kind of scenarios. Those speed maps are actually maintained by different DOTs. Again, it's a very interesting subject to pursue, but we just didn't do that in this study. Yeah, but with all those curves, if you have a good map of speed zones, for example, you can very quickly identify where are the things that are fall behind. So
Thanks a lot.
Any other questions? Yeah, I don't see anybody else unmuting themselves. Cheng-Bo, thank you for a great presentation. I'm sorry we kept you to just 30 minutes. I hope people go look at your publications because I'm sure there's a lot more information out there. And the report for this project will be on the SaferSim website. If you were a little bit late coming in, we've recorded this and we'll be posting it on our YouTube channel, and then everyone will get an email about that. So again, thank you very much. And thank you for your kind words about SaferSim. SaferSim has been near and dear to me for 10 years, and it really is a family. So it's very glad to have you around and have you working with us.
thank you.
Okay, so thank you, everyone. And with that, we'll say goodbye.